In this video, we're going to be talking about the fundamental theorem of calculus. It has the name fundamental in it, so it's probably pretty important. Often abbreviated to FTC, the fundamental theorem of calculus establishes a connection between the two branches of calculus, which are differential calculus, or the tangent problem, and integral calculus, or the area problem. They might seem unrelated, but in fact, they are inverses of each other. Before we look at the fundamental theorem of calculus, let's explore a new type of function. Consider the function g of x, which is equal to the definite integral from a to x of some function f of t dt, where f is a continuous function on the closed interval from a to b, and x varies between a and b. Although this formula may seem like a strange way of defining a function, the subjects of physics, chemistry, and statistics are full of such function. So here we have defined g of x to be essentially a function that looks at some other function and the area underneath the curve. So when I input a value into g of x, say for example I'm evaluating g of 4, that means that we are looking at the definite integral from a to 4 of this function f of t. So in this example, we would replace x with 4, and then from a to 4, we would find the area underneath the curve of f of t. Let's go ahead and look in an example. Example 1 says, let g of x equal the definite integral from 0 to x of the linear function negative 1/2 t plus 1 dt. Part A says graph y equals negative 1/2 t plus 1 and use the concept of net area to evaluate the following inside of our table. Let's go ahead and graph our linear function to start off. So we have y equals negative 1/2 t plus 1. That means that we have a y-intercept of 0, 1, and then our slope is negative 1/2. So we go down 1, right 2 units, and then down 1 and right 2 units. All right, so we've graphed our line, and off to the side here, we want to go ahead and evaluate these specific x values into our g function. Now be careful, we are plugging these x values into g and not into the linear function y. So if I wanted to evaluate g of 0, that would mean that I am evaluating the definite integral from 0 to 0 of negative 1/2 t plus 1 dt. Now, in a previous section, we learned that when we're calculating a definite integral and the limits of integration are the same number, then that means that we have 0 as an output. So now let's go ahead and we want to evaluate g of 1. So that means that we're calculating the definite integral of our function between 0 and 1. This means that we want to calculate the area underneath the curve between the x values of 0 and 1. So here is 0, and here is 1, and I want to find the area underneath the curve of this shape. Now, this shape is a trapezoid, so we could find the area by thinking about it as a trapezoid. What you could also do is you could split this up so that the top portion is a triangle and the bottom portion is a rectangle. So in order to figure out the area of the triangle and the rectangle, we need to figure out this value. In other words, that's the value we get when we plug in 1 into our linear function. Negative 1/2 times 1 plus 1 ends up giving us 1/2. So for the triangle, that means that this dimension is 1 unit, and then this is 1/2, and this is also 1/2. So for the triangle, the area of a triangle is 1/2 base times height So that's the area of the triangle. And then for the area of the rectangle, it's the base times the height. In this case, the base is 1, and then the height is 1/2. So if I multiply those together, I get 1/2. And I want to add these two numbers together, and 1/4 plus 1/2 is 3/4. Okay, so that means that when I plug in 1 into my g function, my output value ends up being 3/4. Now we'd like to evaluate g of 2, so I'm looking at the area underneath my linear function between 0 and 2, and if I shade in this region, that one's a little bit easier than the previous calculation because this is just a single triangle, and its height is 1, and its base is 2. So the area of a triangle is 1/2 base times height, which in this case is 1/2 times 2 times 1. So that area is 1. Now we want to evaluate g of 3, so we are looking at the area underneath the curve between 0 and 3. And notice that between 0 and 2 we have that triangle that we drew previously, and then from 2 to 3 we have a triangle as well, but that triangle is underneath the x-axis. And something else that you'll notice is this is symmetric here, and so here this triangle has the same area as this triangle. One is below the x-axis and one is above the x-axis, so they kind of cancel each other out, and ultimately we really just want to calculate this green area here, which we already did in a previous part of our table, and we found that that was 3/4 for that particular trapezoid. So when we evaluate g of 3, our output value ends up being 3/4. Go ahead and pause the video and take a moment to try and calculate g4 or g of 4 and g of 5 on your own. I'll reveal the answers in just a moment. All right, part B of this example asks us to graph g of x. I'm going to graph it in black since we have our output values here in black, and g of 0 is 0, so I'm going to plot a point at 0, 0. Then when I plug in 1, my output value is 3/4. When I plug in 2, my output value is 1. Then when I plug in 3, my output value is 3/4. And then when I plug in 4, my output value is 0. And finally, negative 3/4. And when I connect this, I didn't do a very good job of connecting them, but it's supposed to form a parabola. So now part C asks us to graph g prime of x. So one ordered pair that would be easier for us to graph is I have my vertex of my parabola right here, and from calculus or differential calculus we should remember that when you have a parabola and you're looking at the derivative for the x value of the vertex, the derivative should equal 0 because we have a local maximum there, and so we have a horizontal tangent line. So when our input value is 2, our output value should be 0. Now another thing is that if g of x is a parabola, then again from differential calculus, we should know that when we differentiate, then the derivative of a quadratic function is a linear function. So if I'm looking now at some other x values, if I plug in 1, I can see that my tangent line has a positive slope. And when I plug in 3, I should see that my tangent line has a negative slope. Do you have an idea where we're headed with this? So I went ahead and I graphed the rest of g prime of x. So here we have the graph of g prime of x, and then in black here, we have the graph of g of x. So part D says, what conclusion do you think that we can come to if you said that g prime of x and y equals f of t are the same function? Then you would be correct. So g prime of x is the same linear function that we graphed earlier. So that conclusion leads us to the fundamental theorem of calculus, part 1, which says if f is a continuous function on the closed interval from a to b, then the function g, defined by g of x equals the definite integral from a to x of f of t dt on the closed interval from a to b, and that's continuous on that closed interval from a to b and differentiable on the open interval from a to b, then our conclusion is that g prime of x is equal to f of x, which is a very powerful statement. So let's look at example 2, which says find the derivative of the following functions. Part A, we have g of x equals the definite integral from 0 to x of the function 3t minus 5t cubed dt. So based on the theorem that we just learned about here in part A, if I want to find g prime of x, what the theorem says is that g prime of x is equal to f of x. And here our integrand is f of t, so all we need to do is into our function, we would replace everywhere we see a t with the variable x. So here is my integrand. This represents f of t, and inside of it, I'm going to replace all of my input variables with x. So I have 3x minus 5x cubed. And it's as simple as that. That is our answer for part A. So here's where things get a little bit more tricky. The fundamental theorem of calculus part 1 requires that the lower limit of integration be some constant. And remember, a constant is just some numerical value, and that the upper limit of integration has to be just a variable like x or u or t. And so when you have a function as your upper limit of integration that's something other than x, and you have a more complicated function, you can't approach these examples in the same way that we did previously, because again, the fundamental theorem of calculus requires that our upper limit of integration be just a single variable on its own. So, and it can't be a more complicated function than that. So how do we deal with that? Well, let's look at part B. We have capital F of x is equal to the definite integral from negative 2 to 3x of the integrand negative t squared plus 6 dt. So instead of our upper limit of integration being x, now we have 3x, so we can't quite use the fundamental theorem of calculus part 1 yet. And what we need to do is what we're going to do, we'll say let u equal 3x. And if we do that, this implies, so this arrow thing means implies. So this implies that the derivative du dx is equal to 3. So now what I want to do is I want to take the derivative with respect to x of the definite integral from negative 2 to 3x of negative t squared plus 6 dt. This is the same thing as, instead of taking the derivative with respect to x, now I'm going to take the derivative with respect to u. And in my definite integral, we said that we want to let u equal 3x. So I'm going to go ahead and substitute u into my upper limit of integration. And this idea is going to come from differential calculus. If I'm taking the derivative with respect to u, I need to multiply this by du dx, and this idea is coming from chain rule. And one way that you can think about this is, remember, d du and du dx are not fractions, but they kind of behave like fractions. And so if you multiplied them, again, they're not fractions, but if they were, if you multiplied them together, what would happen is the du in the numerator and the du in the denominator would cancel out, and it would return to this fraction here. But again, they're not fractions, they just happen to behave like fractions. So this idea here where we're taking the derivative with respect to u and then multiplying by du dx is coming from the chain rule. But now that we're taking the derivative with respect to u and our upper limit of integration is just a single variable on its own, at this stage, we can now use the fundamental theorem of calculus. So the thing that I just underlined, that squiggled underline, based off the fundamental theorem of calculus, all I'm doing is, in my integrand, everywhere I see a t, I can now replace it with u. And then I need to multiply this by du dx. So our final answer needs to be in terms of x. So originally we said let u equal 3x. So what I'm going to do is I'm going to substitute 3x back in. And so I get negative 3x quantity squared plus 6. And then this needs to be multiplied with the derivative, du dx. So I'm going to multiply that times 3. And if I wanted to simplify that a bit, if I squared 3x, that would give me 9x squared. And I'm multiplying that by negative 1. And then we can distribute the 3 in. If we did that, we'd get negative 27x squared plus 18. And this represents our final answer. All right, let's move on to part C, where we want to find g prime of x. And once again, our upper limit of integration is not just x by itself. In this case, it's x cubed. So we're going to apply the same strategy. Off to the side here, I'm going to say let u equal x cubed. And then if that's the case, that implies that du dx is equal to 3x squared. So I just took the derivative of that. So I want to take ddx, or the derivative with respect to x, of the definite integral of 1 to x cubed of the natural log of t dt. And so that is, because of chain rule, the same thing as the derivative with respect to u of the definite integral from 1 to u of the natural log of t dt. And then I just need to make sure that I multiply that by du dx. And again, thinking about this going backwards, again, ddu and du dx are not fractions, but if they were, the numerator and the denominator of du would cancel each other out, and we would return to d over dx. So now that we have our upper limit of integration as a single variable on its own, we can apply the fundamental theorem of calculus part 1, which tells us that in our integrand, we're just going to replace everything with our upper limit of integration. And then I would multiply by du dx. And we need our answer to be in terms of x. So instead of keeping this as u, I'm going to replace it with x cubed. So I have the natural log of x cubed times our derivative function. And I just like to have the 3x squared in front of my natural log, so I'm going to rewrite that. And this represents our final answer for part C. All right, for part D, we once again want to find g prime of x. And the difference in this scenario is that our upper limit of integration is a constant, and our lower limit of integration is a function. And So we learned a property in the previous section that allows us to rewrite this. And so if you don't remember, that property tells us that we can swap the limits of integration and it would be equal. We just have to make sure that we multiply our integral by -1. So everything else stays the same. We just swap the limits of integration and multiply the entire integral by -1. And then now we've defined our g of x to be this. So now our upper limit of integration has a variable, it's a function, but it's not just x by itself. So we'll again have to use the same methods we were using for the last two examples. So I'm going to say let u equal x squared. That implies that du dx is equal to 2x. So if I wanted to take the derivative with respect to x of -1 times the definite integral from 1 to x squared of our original integrand, I would need to switch this. So now I'm taking the derivative with respect to u, and I'm going to replace x squared with u. And I'm multiplying by du dx at the end. So now in this first part here, I can use the fundamental theorem of calculus part 1. So that's going to give me negative. And then everywhere I see a t, I'm going to replace it with u. Okay, and then we have negative, and I want to substitute x squared in for everywhere I see a u. So that's going to give me x squared to the 4th power plus 1 over x squared quantity squared plus 1. And then I need to multiply this by 2x. And if we do some simplification, that is going to be negative 2x times x squared to the 4th power is going to be x to the 8th power, because I multiply the exponents together. And then x squared squared is x to the 4th power. And this represents our final answer for part D. Now, a question that I often get asked is, do we have to show all of the steps where we're applying chain rule like we needed to in parts B, C, and D? And to that, my answer is no, you don't have to show that every time. So really, the secret sauce is that, for example, for part C, if you wanted to evaluate g prime of x in your integrand, what you're going to do is anywhere you see a t, you're going to replace it with whatever the upper limit of integration is. So in this case, that would be the natural log of x cubed. And then you would just need to multiply that by the derivative of the upper limit of integration. So that would be 3x squared. And this was the same answer that we got previously, just writing out all the justification for it. So I'm okay with you just writing this out. And then for part D, if we rewrote it with the negative, so again, I'm going to rewrite this. I have the negative sign, and then anywhere I see a t, I'm going to replace it with my upper limit of integration. So that would be x squared to the 4th plus 1 over x squared squared plus 1, and then I just need to make sure that I multiply this entire thing by the derivative of my upper limit of integration, which would be that. And once again, that gives us the same answer that we got previously. So that's a bit of a shortcut to getting our correct final answer.